Well, it is our program for today. Let's start with the last one, 9-point circle theorem. We need to show that in any triangle, 9 different points belong to the same circle, like this one. So we have a triangle ABC, 9 points belong to the same circle. Let me draw a picture and we will see what we need to show. Any triangle, 9 points belong to the same circle. Let's draw altitude here. So one altitude, another altitude, and another altitude. 3 altitudes. So there is no question at the moment that if you take feet of altitudes, that these 3 points belong to the same circle. No question about it. But besides these points, also you have a midpoints of these segments. Midpoint of this segment, midpoint of this segment, midpoint of this segment. All of them also belong to the same circle, and midpoints on the sides of your triangle. So this side midpoint is here, this side midpoint is here, and this side midpoint is here, and all these 9 points, they belong to the same circle, and that's what we need to show. So the problem is really very simple, only if you make a right approach to solve it. Well, the wrong approach, if for example you don't have enough of experience with geometry, would be just to connect these points. You would have a lot of different segments, and after that the picture will be super messy and it will be very difficult to understand how to solve the problem. So the main question that we need to ask here, how many points do we need to uniquely define the circle? And of course the right answer is 3 points that do not belong to the same line, and it means that we can take any 3 of these 9 points, for example this point, and this point, to consider triangle if we connect these points, and after that we consider circumscribed circle of this triangle, and we will show that other points also belong to the same circle. And in geometry it's very realistic approach, because for example if you have some triangle, I chose for example 3 of these points, and how can I show that some other point belong to the circumscribed circle of this triangle? Very simple. For example, if we have a point here, we can show for example that we have 2 equal angles. If this angle here is equal to this angle, then it means that all these points belong to the same circle. It's one way. For example, if I take a point here, I can show, I can prove that this angle plus this angle, if the sum of these angles is 180 degrees, it means that all these 4 points also belong to the same circle. And this is it. So the only question for me here, which points should I choose? And the right answer is, it makes sense for me to choose the feet of altitudes. If I choose this one, and this one, so I will consider the circumscribed circle of this triangle, and after that what should I do? I will show that this point, the midpoint on this side, belongs to the circumscribed circle. How would I show it? Well, I will just connect this, and I will show that these 2 angles are equal, and if it is true, if I showed it, it means that this point is on the circumscribed circle, but the proof is exactly the same for this point, and the proof is exactly the same for this point. It means that all these 3 black points and these blue points that are feet of altitudes, they are on the same circle. And after that I will just go back to my basic red triangle, and I will consider for example one of these points, midpoint on this segment. And what should I do here? I would just prove that this angle plus this angle is 180 degrees, and this is it. It means that all these 4 points are on the same circle, and the proof is exactly the same for this one and for this one, and this is it. So the problem will be solved. So let's start from our basic triangle that connects feet of our altitudes. Let's make a little bit bigger picture. Now we know what path should we go, and it will make our solution much faster and much easier. So now we have altitudes here. Okay, we don't even need to make any letters like ABC. So my main question for you, as we started with this triangle, how to find this angle in terms of angles of your triangle. For example, if this one is alpha, if this angle is alpha, how to find this angle? Well, the answer is really very simple. If you know basic geometry, when you draw altitudes, you have a situation that this angle is similar to this angle, to this triangle, small triangle, is similar to bigger triangle. It means that this angle always equals to this angle, and this angle is always equals to this angle. By the way, why is it true? It is true because when you draw altitudes here, you have 90-degree angle, 90-degree angle. These angles are both 90 degrees. It means that equal angles, and these 4 points, they belong to the same circle. And by the way, if there is a 90 degrees, it will be a diameter of the circle. But the main thing for us that this quadrilateral is inscribed in the circle, and if this is alpha, it is 180 minus alpha, and it means that this is alpha. And similarly here, if you have beta, this one is 180 minus beta, and this is also beta. So, but we will need only alpha in this case, so we cannot take beta into account. So let me delete beta, and this is alpha, and this is also alpha. Once again, because this small triangle is similar to the big triangle. And the angle that we need here is 180 minus 2 alpha. Okay, it is the first thing. Obviously, what we need to do here, we need to take, for example, midpoint on this side. For example, let's assume that it's here, midpoint of this side, and we connect it with these two points, and we need to show equal angles. So we need to prove that this angle between black segments is the same as this angle here. And the geometry here is super simple. If you connected the midpoint with this point, it means that in this right triangle, this one is median, and median in the right triangle is always the half of hypotenuse. Once again, why is it so? Why median is always the half of hypotenuse? This is the right triangle. You consider circumscribed circle. This angle is 90 degrees. It means that in the circumscribed circle of the right triangle, this one is the diameter, and median, it just comes to the point in the middle of the diameter. It means that this is the center of the circle, and it means that this is a radius, this is a radius, and this is a radius. So the proof is very simple. It means that if we consider this right triangle, this is a half of the median, and in this right triangle, this is also a half of the median. And it means that this is an isosceles triangle, and it is also an isosceles triangle. And after that, it becomes super simple for us to find this angle, because we will find maybe this angle in this isosceles triangle, in this isosceles triangle, this one, and after that we will take 180 and subtract these two angles. And the process now is just pure algebra. There is no real geometry here involved. So we mark, for example, we don't know this angle, and we mark it as gamma. It means that this angle is gamma once it is an isosceles triangle. So this one is beta, and this one is also beta. This one is beta, right? Because it is an isosceles triangle. This is it. So this angle is 180 minus 2 gamma here, and this angle is 180 minus 2 beta. And in order to find the angle that you need to take 180. It's like a straight angle minus sum of these two angles, 180 plus 2 alpha. 180 minus 2 gamma plus 180 minus 2 beta. And after simplification, you will get 2 gamma plus beta minus 180, like this. But what is gamma plus beta? Remember that gamma, beta, and alpha, they are all angles of the bigger triangle. It means that gamma plus beta is actually plus alpha, it's 180 degrees. It means that it can be expressed as 180 minus alpha, because gamma plus beta plus alpha is 180 degrees. It means that gamma plus beta is 180 minus alpha, and if you substitute it here, you will get 2 times 180 minus 180. You will get eventually 180 minus 2 alpha. This is it. So it means that this angle, eventually 180 minus 2 alpha, it is the same as this angle. And what you have that this angle equals to this angle, and eventually all these 4 points belong to the same circle. Once again, as we told here, it is we have a proof for this point. For this point it will be exactly the same, but we will have to consider this angle, and for this point it will be exactly the same. So now we can conclude that all these 6 points, black and blue, belong to the same circle. Eventually, we now need to consider one of these points that is in the midpoint between vertex and orthocenter. Orthocenter is where altitudes intersect. So let's make a new picture. We have no problem to make a new picture to make everything much more clear. Let's consider our triangle. Again, we draw it here. We have altitudes intersect at the same point. Our base triangle is here, so it is our main triangle. Okay, and we need to consider some other point. So I can choose which point to consider, and in my understanding, it makes sense for me, for example, to consider this point. So I take the point that is in the middle, the midpoint of this segment, and I need to show that this point belongs to the circle that is circumscribed circle of this red triangle. And I need to show in this case that this angle plus this angle is 180 degrees. So let's try to do it. This angle plus opposite angle, if their sum is 180, then everything is true, and basically my problem will be solved. Once again, we will go to basics. We remember from the previous one that if this one is alpha, if this one is alpha, let me make it a little bit more clear here. Just a second. So I will mark here. Yeah, it's a little bit better now. This one is alpha. It means that this one is 180 minus 2 alpha. If I can show that this angle is 2 alpha, it means that this angle plus this angle is 180 degrees, and that's what we need. Why this angle is 2 alpha? Well, the reason is super simple. Look at this right triangle. This is midpoint of hypotenuse. This is a median. It means, again, that this is the half of hypotenuse. This is the right triangle, this is hypotenuse, this is a median. And the same is here. What we have? Hypotenuse, right triangle, median. And after that, it is an isosceles triangle. What can we say here? We can say here that this small angle equals to this small angle, and this small angle equals to this small angle. This is a line. It is an external angle of this isosceles triangle. This angle is a sum of these two angles. For example, this small angle is y and this small angle is y. So this small angle, external one, is 2y because it's y plus y. In this isosceles triangle, this is an external angle and it is the sum of these two small angles. It is x and x, and this one is 2x. So this angle is 2y plus 2x, 2y plus 2x, but at the same time y and x, sum of these angles, is actually your angle alpha, here, and it means that this is 2 alpha, and sum of these angles is 180 degrees. This is it. It looks like everything is perfect, but there is a main thing here. We only consider the case of acute angle triangle. We haven't considered the case when we have one obtuse angle. In this case, the altitude, in our case, they intersect inside the triangle. Yeah, and it was like a foundation for us to make all these pictures. But it may be the case that these altitudes intersect outside of triangle, and we need to quickly consider this case. It will be super simple, but to finish and to complete our solution. So let we have a situation when you have an obtuse angle triangle like this one, and let's extend this side, let's extend this side, and in this case what we have that altitudes, they intersect outside of our triangle. Let's draw one altitude, let's draw another altitude. I hope it works, and the third altitude will look like this. So let me mark 90-degree angles here, 90-degree angles, 90-degree angles. So my main triangle, very important, is ABC. My main triangle is ABC. The orthocenter is now outside of our triangle, it's H. And let's mark precisely what we need to show here. Let's mark 9 points that we are talking about. Okay, triangle ABC is a triangle that we initially have. We need to show that the feet of altitudes of triangle ABC, it's the first 3 points. Okay, so now 3 points here. This point, this point, this point. They belong to some circle, okay? These 3 points. Next 3 points. The midpoints that connect orthocenter with vertices, midpoints of segments. We connect orthocenter with vertices of our triangle and we take midpoints. Orthocenter is here, we connect it with the vertex, and midpoint is here. Okay, orthocenter, let's mark that this midpoint. Orthocenter, we connect it with vertex, midpoint is here, okay? And orthocenter connected with vertex A, midpoint is somewhere here. Great. These 3 points and midpoints of the sides of triangle ABC. ABC. Midpoints on the sides. The midpoint on BC is this point. The midpoint on AB is this point. And the midpoint on AC is this point. Let's mark it somewhere like a circle and circle. It's midpoint and this one. We need to show that these 3 points, these 3 points, and these 3 blue points, that they belong to the same circle. But now, if you look closely to the picture that we drew here, there is not even question that it is true, because you should consider, instead of your triangle ABC, as you can see, we marked here all our 9 points. Instead of triangle ABC, consider triangle AHC. AHC. This is already not obtuse angle triangle. This one is obtuse, but AHC is acute angle triangle. Why? You can see its altitudes, AHC, altitudes intersect inside the triangle. And instead of triangle ABC, you say, I consider triangle AHC. It is acute angle triangle because you can see its altitudes intersect inside the triangle. And for this triangle AHC, once it's acute angle, everything is already proved. It has 9-point circle. And if you consider all these points that we marked here, these are exactly, precisely all these 9 points for 9-point circle of triangle AHC. Really, let's consider. For example, what is this point for triangle AHC? This point for triangle AHC. It is the midpoint of the segment that connects vertex H with orthocenter B, because B is orthocenter here. Midpoint. It is one of the points of on the 9-point circle. Let's go to another one. We consider the midpoint of HC. Midpoint of HC. What is this point? This point is exactly the middle point of the side HC. This point is exactly the middle point of the side AH, and so on. And what is this point for triangle AHC? Once again, this one is a midpoint of the segment that connects vertex A with orthocenter. What is this point? This point is the midpoint of this one, and these are fits of altitudes. So the points that we're interested in, 9 points for triangle ABC, are exactly the points of acute angle triangle HC. These are 9 points that belong already, as we shown, for 9-point circle. And this is it. So it completes our solution, and now we can finally go to the next problem. Our next problem is Euler's line theorem. Let me explain you quickly what do we need to show here. We need to show that in every triangle, 3 very specific points always belong to the same line. And these points, at first, it is the center of circumscribed circle O. Let me mark it here. O is the center of circumscribed circle. M is the point where medians intersect. Here it's marked as a centroid. G is the same, the point where medians intersect. And the point H where altitudes intersect. Let me make it a little bit further, like this one, H. These 3 points, we should show that they always belong to the same line. And moreover, that OM divided by MH is 1/2. It means that if this one is X, this segment is X, that this segment should be 2X. So O, center of circumscribed circle, M, point where medians intersect, H point where altitudes intersect, and if this one is X, this one should be 2X. So very simple problem, as you can see, but simple to understand. And what would be the right approach to solve it? The right approach is to keep our picture as clean as possible, and after that try to maybe define positions of these points. For example, the position of point M can be defined only if you draw one median here, and the M divides this median with relation 2 to 1 from its vertex. So it's not a problem at all for us. O is very easy to define the position of the center of circumscribed circle just by making this perpendicular. And as you can see, we don't need to draw here all the altitudes, all the medians to connect this point O with all the vertices, because in this case we will have very messy picture and the problem will be pretty unsolvable. So let's make it clear, and let's start from the simplest part of this problem, from the position of M. M is once again point where medians intersect. So let's mark this one. Let's make this one equal, and M is located somewhere here. This one is 2X and this one is X. What we need to understand? We need to understand that also the position O of the center of circumscribed circle is very easy to define, because it is located right above the center point of this segment. And it's easy to understand if, for example, you connect O with two of the vertices, you will get immediately isosceles triangle. So this triangle is isosceles, and this equals to this one. It means that, let me mark it with, yeah, this one equals to this one, and if you bring here altitude from point O, it should go exactly to the middle of this segment, and it means that the median and this perpendicular go exactly to the same point of this segment. It's very helpful, it will be helpful for us, so it is a perpendicular. So how to define this, for example, this altitude? Usually it can be done like this. So if this one is R, this one is R. Usually R is expressed in terms of A and opposite angle alpha. We use sine rule. We say that A over sine alpha equals to R, and after that we can just express R as A over 2 sine alpha. But in our case we can keep it as R. The only thing that if we have an angle alpha here, this angle should be 2 alpha, because it's like inscribed angle in circumscribed circle. This is a central angle, 2 alpha. It means that this one is 90 minus alpha in this isosceles triangle. And now we say that this distance, let's mark it as H, H equal R times sine of 90 minus alpha. R times of sine 90 minus alpha. But sine of 90 minus alpha is exactly cosine alpha. It means that R cosine alpha. So this altitude is R cosine alpha. Let's delete it, and just instead of it we write R cosine alpha. Okay, this one we have. Now we need to define the position, because once again this position is defined. O is located right above our segment, right above the central point of our segment on this distance. M is also kind of defined because it's a median 2 to 1 from the vertex. It's this construction uniquely defines this position, and now we need to go to the orthocenter or to point H, and maybe to draw several altitudes to define this position. It's obviously that we don't need to draw all 3 of altitudes in most of cases, but because 2 altitudes intersect at one point, and it's enough to define the position of H. So let's draw some 2 altitudes here, maybe like this one, maybe like this one here, and this one here. 2 altitudes. H is located at this point. So H is here, and H is here. We need to show that these 3 points are on the same line. Okay, so the main thing here that I want maybe to find this the distance like this one or the distance like this one. And after that, it will be also very good result, because if I have, for example, this distance, I know that h is on the perpendicular line, and it will be this distance from this one. So what I found, that it will be much easier in this situation to find this distance. And now we will show that this distance is twice this distance. So it means that, for example, if let's mark this as AH, this segment AH is always 2 times this segment, is always 2r cosine alpha. So this segment is always twice the segment. How to do it? Well, in order to find this one, we should consider this quadrilateral. So in this case, in very rare cases, we need to draw like third altitude. And why we do that? Just because this quadrilateral is very good, very good looking, if we say, because what happens here, that this AH is a diameter of circumscribed circle here, because look at this quadrilateral, opposite angles are 90 degrees, there exists a circle that passes through all its vertices, and AH would be exactly the diameter of this circle. And in order for me to find AH, I can, for example, take this triangle or this triangle, find the radius of circumscribed circle of this triangle using sine rule, and after that I will find this diameter. And the best scenario here, if I want to express everything through RA alpha, is to look at this small triangle. As we already told in the previous problem, this small triangle is always similar to the bigger one, and the coefficient of their proportionality is exactly cosine of this angle. It's very easy to understand, because, for example, if this side B, let's look at this right triangle, this side of this triangle from this right triangle, this is B, this is alpha, it means it is B times cosine alpha. This would be B times cosine alpha, if this is B. If this is C, it means that this one is C cosine alpha from this right triangle. And you can see that not only they are similar, their coefficient of proportionality is exactly cosine alpha. What does it mean for us? It means that if this one is A, this one is A times cosine alpha, A times cosine alpha. And if we want to find the radius of circumscribed circle for this triangle, we will use sine rule for it, and we will say that A times cosine alpha divided by sine alpha is 2 radius of circumscribed circle for this one, for this triangle. It's 2 rho, where rho is the radius of this triangle, and 2 rho is actually the diameter. The diameter, as we can see here, AH, the diameter AH, so it will be like AH equals A times cos alpha divided by sine alpha. But do not forget that A divided by sine alpha is 2 radius of circumscribed circle in our bigger triangle. So we can separate this portion, and after that we get that AH really 2r times cosine alpha. So after that, when we have this situation, our problem becomes like super simple, because this distance is r cosine alpha, this distance AH is 2 times larger, and we can actually throw away everything despite all these points OHM, and we can redraw our picture in much simpler way. How to do it? Let's use again red color as we used previously. Here the position of A, it's our altitude AH. Let's mark it here. Okay, AH is here. Here is A. Let me mark H a little bit lower. Just A is here. This one is 2r cosine alpha. The other point is the center of circumscribed circle is here. It's O, and this distance we already figured out that it is r cosine alpha. And the point M, it's on this median. Let's make a median here, and the point M divides this median here with relation 2x to x, 2x here and x here, 2x x. And now it's very easy to understand why these points HMO belong to the same line. So in order to do it, we need to forget for a second about the point M, how to show that they belong to the same line. So let's forget the second for about the point M that we marked here. We only mark O and H. And let's notice that these lines are parallel, of course, because they're perpendicular to the same line. Let's connect here these 2 points. These 2 triangles are similar. Moreover, this triangle is 2 times larger, this triangle is 2 times larger than this triangle. It means that their corresponding sides, for example, in front of this angle and in front of this angle, there's a corresponding sides, and this is 2 times larger than this one, and this one is 2 times larger than this one. So let's mark it. If this one is 2 times larger, then it means this is, for example, 2y, and this is y, and this is, for example, x, and this is 2x. And we got that this point divides our median with relation 2 to 1 from its vertex. It means that it's exactly the point M, because there is only one point on the median which divides it with the given relation. It means this is a point M, and we actually proved everything we needed. Look, O, M, and H are on the same line, and we actually got that OM is x and MH is 2x, and this is it. It completes the solution of our problem. But once again, what I want to emphasize here, that it completes the solution of our problem only in the case of acute angle triangles. Now we will consider the case of obtuse angle triangle, and I think it will be a really cool geometry. Because it will be a little bit more advanced than we did before. So now we have an obtuse angle triangle. I already draw it as these 2 sides are extended. As you can see, this is obtuse angle triangle, and our main triangle is ABC. And now the problem is that altitudes, they intersect outside of our triangle, not like in the previous case when they intersected inside, and we could use this picture and this geometry. Now we have the situation that we should extend the sides of our triangle, and we should draw altitudes like this, and eventually this one will be, the last one will be also altitude, this one. Let's mark that our degrees, this is 90, this is 90, and this is 90 here. Okay, so now orthocenter of our triangle ABC is located here. It's a point H. Okay, it's passes through B, and let's understand which points should belong to our Euler's line. So orthocenter is H for this triangle. What would be the point where medians intersect? Well, here it looks like in this triangle we should again draw a median, like in the previous case, maybe this one. It divides this side in half, and we take here points that divides this median with relation 2 to 1 from its vertex, 2 to 1, and this is a point M, the point where medians intersect. So this one, and finally we need to look at the center of circumscribed circle for triangle ABC. Because this triangle has an obtuse angle, this one, the center of circumscribed circle also outside of our triangle. And we know that nevertheless it is on equal distance from these points, and this center is kind of right above, right below, in this case, the center point of this segment. Because once again, if I take the center O of circumscribed circle here, O, these segments are the same. If I draw perpendicular, it will be like exactly perpendicular bisector to this segment, and O is located somewhere here. And what we need to show now that H, M, O are on the same line. And of course we could consider this one as a separate problem in geometry, but what I offer to do is to use our previous results. We already have result that Euler's line exists for acute angle triangle. And this is amazing because this triangle, this one, is definitely AHC is acute angle triangle, because all these altitudes, they intersect inside of our triangle. And we can use the fact that Euler's line exists for this triangle, and after that we will see how Euler's line for this triangle can be obtained from Euler's line for this triangle. And it's not like as complicated as it sounds, but it's really cool because we'll go to a little bit more advanced stuff here. Let's look to triangle AHC and let's understand how Euler's line for this triangle really looks. Okay, first, it passes, for this triangle, we know that it exists. It passes through its orthocenter. Oh, by the way, orthocenter of this bigger triangle is exactly point B. Okay, so Euler's line passes through this point. Next one, it passes through the points where medians of this triangle intersect. Well, in order for me to find the points where medians intersect, of course, it's very convenient for me again to take the midpoint here and to draw only one median. Only one, like this one, and I take point on this median that divides this that divides median with a relation 2 to 1 from its vertex. So I'll take this one, and it will be 2y over, let me mark it, it's a little bit lower, maybe here, 2y, this segment is 2y, and this segment is y. So this is a point M, let's make it M1, let's make it M1 for the point where medians intersect inside the big triangle. And finally, the center of circumscribed circle of big triangle, AHC. How to mark this point? Well, it's obviously again above this midpoint O, and it's on the distance that we can calculate. But once again, let's just mark this point O here. This point O here, it's the center of circumscribed circle of the big triangle. And don't look at the picture; it may look a little bit messy at the moment. We will simplify it. So we know for sure that these 3 points B, M1, and O, they belong to the same line because it is an Euler's line for acute angle triangle AHC. And what we will do now, we will see how Euler's line for bigger triangle is connected maybe to Euler's line for this triangle. How to get these points H, M, O from these points that we have here, and you will see that we will get very simple geometry at the end of it. So let's look what we have. For example, what is the connection between B and H? B is orthocenter of big triangle, and H is orthocenter of this triangle. What is the connection? Well, H is higher, this sort of perpendicular distance, perpendicular to the segment. H is higher. And what is this distance? From the previous problem, we know that this distance is exactly, we can write it as 2r cosine alpha. Am I correct? So this distance is 2r cosine alpha. Yes, where alpha is this angle, A is this side, and R is the radius of circumscribed circle of this big triangle. Great. So now we will make a picture nearby where we can separately mark our points. So this line is purple. Let's use also purple line here. And here we mark point B, and we mark point H on the distance above, and this is like a perpendicular distance to perpendicular line to this segment. So we go straight up, and this one would be 2r cosine alpha. 2r cosine alpha. So it is the distance between orthocenter of the big triangle and orthocenter of a small triangle. Great. Let's go to the next one. M1. Okay, M1 would be, let's really make it here because it should be 2 to 1, right? M1. And what is the distance between medians intersection of a big triangle M1 and medians intersection M of a smaller triangle? Let's look at this one. It's easy to understand that what is M1? M1 divides this purple line 2 to 1 from its vertex. But by the way, M also divides this red line with relation 2 to 1 from its vertex. And it's easy to understand that M1 is not kind of midline, but this line is parallel to this altitude. Once again, let's look at this triangle. M1 divides this side 2 to 1 from its vertex, and point M also divides this side 2 to 1 from its vertex. It means that this small triangle and this bigger triangle, like very narrow triangle, this one and this one, they are similar. And what is their coefficient of proportionality? You can see that this one is x, this one is 2x, this one is y, this one is, I'm sorry, this one is x, and this one is 3x, this one is y, and this one is 3y. So this is 3 times smaller than bigger triangle, and it means M1M is 3 times smaller than parallel corresponding side BH. 3 times smaller, it means that it's 3 times smaller than BH. And let's mark here M, and here we obviously go down on our picture, down on M, and this line, we will mark it as blue. This one is parallel to this one. Why parallel, by the way? Because similar triangles. This one, M1M, parallel to this line, and it will be 1/3 of this one, 1/3. It will be 2/3, 2/3 r cosine alpha. Okay, so I think it's correct. And finally, it is a relation between M1 and M, between medians inside, where medians intersect in a big triangle and medians intersect in a small triangle. And finally, the last point, O. It is, on the one hand, O is the center of the circle of a big triangle, of circumscribed circle, and O, let's mark it O1 here. And this is the center of the circle of this triangle. How are they related? So, do you remember that in a previous problem, when we marked this distance in acute angle triangle, this is r cosine alpha. So in our case, we can also mark this one as r cosine alpha. Okay, but what about this one? We know that this point is on equal distance from this A and C. By the way, do you realize that OC and OA are also equal r? Why OC? Why the radius of the circumscribed circle of triangle ABC is exactly the same as r? It's very easy to understand by applying sine rule to triangle ABC. If you apply sine rule to triangle ABC, you will see that the radius of circumscribed circle for this triangle is A divided by sine of this angle. Two radiuses. To r is A divided by sine of this angle, but this angle equals to this angle, and this angle is 180 with this angle. Basically, if it's alpha, it's 180 minus alpha, and this is 180 minus alpha, and when you divide A divide by sine 180 minus alpha, sine of this angle, this is exactly the same as sine alpha. It means that A divided by sine alpha, so the radius of circumscribed circle, this is double radius, but the radius is exactly the same as r here. So this is r, and this is r, and this distance, and once again it's the isosceles triangle, this distance, what should it be? So we need to understand what is this distance. Well, my main assertion would be that it's also r cosine alpha, that it is the same as for this triangle. Well, why is it true for us? Why is it true? So let's mark it, for example, as r, and we will use just very simple ideas in geometry. For example, we consider the circle that is circumscribed circle for this triangle. This one is 180 minus alpha. This is alpha, 180 minus alpha. This arc, big arc of this circumscribed circle is double of this angle. So it means if this is 180 minus alpha, this big arc will be 360 minus 2 alpha. It means that smaller arc, this one, of this triangle would be exactly 2 alpha, and this central angle here would be exactly 2 alpha, and it means that this one is 90 minus alpha, and it means that this perpendicular from this right triangle would be r times cosine 90 minus alpha, times sine, r times sine 90 minus alpha, it would be exactly r cosine alpha. What does it mean? It means that the distance O1O, r cosine alpha plus r cosine alpha, and let's mark it here on our picture. We're almost done, by the way. The most difficult part is over. So we have here points O, O1, and this distance is 2r cosine alpha. Let me write it so I have enough space. So what we need to notice here, that this is definitely a line. This is definitely a line. But for us now, the main question, if this point, and this point also belong to the same line, this one, and this one. Okay, now we should notice immediately that these lines are parallel. All these lines, this is perpendicular to AC, this one is also perpendicular to AC. M1M, we also told that it's parallel to BH, and it's also perpendicular to AC. Why all these 3 points belong to the same line? And as earlier, in order to show it, we need to forget about point M. So again, we need to forget about one point to show that we have what we need. Let's forget about point M. We know for sure that this one, for example, for Euler's line, this one is x, and this one is 2x. There is no question. It is an Euler line for this big triangle. Okay, let's just connect these 2 points. We connect these 2 points like this, and what do we have? This is parallel to this one, and this is equal to this one. So this triangle, they're not just similar, they're actually equal, because these two are equal and parallel. It means that this side is equal to this side, but for us what's very important, that this side is equal to this side. If this side, this total side is 3x, it is divided by this point into 2 equal parts. It means that it is 1.5x and it is 1.5x. Let's mark it here. Let's just mark here that we are almost done. 1.5x, and this one is also 1.5x. Okay, and now what we are doing, that we make this parallel line from the point M again. So now we just make parallel line from point M that is parallel to this line. This is a parallel line, and we are almost done. What happens here? If we draw parallel line from the point M, what would be the length of this portion? Once again, this line is parallel. It means that this small triangle is similar to the bigger triangle. Okay, what would be the ratio between these two triangles? Let's look closer. This one is 0.5x, 0.5x, because it's 1/2, 0.55x, and the total side is 1.5x. It means that this small triangle is 3 times smaller than this big triangle, 3 times smaller. This small triangle is 3 times smaller. It means that this side, corresponding side, is 3 times smaller than this triangle, and it means that this side here should be 2r cosine alpha over 3. But it's exactly what we had. It's exactly what we had from the previous one, because M1M was the distance the distance that is equal to this value. It means that if it goes parallel, this is the length of this segment. It means that point M exactly on this segment. Point M belongs here, and these 3 points, O1, M, H, they are all belong to the same line. Well, and after that you can say that there is also, just from basic similarity of the triangle, from the parallel lines, you can get also the same situation with ratio, that you will get that one segment is 2 times larger than the other segment on this Euler's line. Well, it was a little bit more advanced. As you can see, what we did, we used the existence of Euler's line for this big triangle with acute angles, and we derived from it the existence of Euler's line for this smaller triangle. Okay, we are near the finish line, we're almost done, and the only thing that we have to prove the last theorem, Euler's theorem about the distance between the center of inscribed circle and the center of circumscribed circle. Let me show you what do we need to prove. So we have some triangle, and it obviously has some circumscribed circle, and the center O, and the radius of circumscribed circle is R. And obviously it has some inscribed circle with center I, it's where angle bisectors intersect. By the way, O is where perpendicular bisectors to segments intersect, just for reference. So angle bisectors intersect at the point I, it's the center of inscribed circle, and the radius of inscribed circle is small r. And this formula provides us amazing connection between the length of this segment, that it can be so easily expressed through capital R and small r in this way. So the length of segment OI can be expressed as R capital times R capital minus 2R. And it looks very simple, and the problem looks initially very simple, but it becomes very complicated if you don't provide the right picture. And here, the proper solution in geometry is a little bit more difficult than we did previously, because in the previous problems, everything that we did was very straightforward. We marked points, we calculated distances, and from the very beginning, it was pretty obvious what should we do next. But here, if you try to do it in a straightforward manner, it becomes very difficult. You will get very difficult formulas if you try to express it like directly, and it's very difficult to come up with this result just by using trigonometry and using some sine rules, cosine rules. This problem becomes like easy only if you come up with the right picture. And let me show you how right picture should look here. So we have a circle, circumscribed circle is here, and we have a triangle inscribed in this circle. It's here. And we have a inscribed circle in this triangle, but we will not draw one more circle. We will just draw angle bisectors because it's enough for us. Let me redraw the last one. The last one should go like this one, and we draw now angle bisectors. This one and this one, they already intersect at I, and this point for us is I, is the center of inscribed circle. O is the center of circumscribed circle. Let it be somewhere here, O. And we need to get this connection, OI, to get this formula through the radiuses of these two circles. What is the difficult part here? The difficult part that it's not obvious why should you do this sort of construction. You should extend OI up to its intersection with the large circle. For me, it was like the most difficult part of this problem. Why should we do it? But if you make this line, it will become a chord of a big circle, and you should also consider this angle bisector, and let's mark that this one is angle bisector, this also angle bisector, and this is angle bisector. And not only you should extend this angle bisector up to its intersection with a big circle, but you also should connect these 2 points and these 2 points. Just a second. Okay, if you know geometry, immediately what's obvious in this picture? For me, it's obvious that this chord equals to this chord, because these inscribed angles are equal. This angle equals to this angle. It means that this arc equals to this arc, and it means that chords that connect ends of equal arcs are also equal. So this one equals to this one. It is a good part. What's next here? Next, we will show that not only these two segments are equal, but they both also equal to this segment. And let's introduce some letters here like A, B, C. For example, this one will be D, and these points of intersection will be X, Y. And I think it's enough for us. Let's delete this small portion here. And we need to show that ID equal to DC. ID equal to DC. Okay, how should we do it? Well, it's really super straightforward here. Super straightforward. We just need to show that this triangle is isosceles and that this angle equals to this angle. And we will just calculate angles in a straight manner. So for example, this one is alpha, this one is alpha. This is inscribed angle, it is equal to this inscribed angle. They are subtended by the same arc, so alpha, this one is alpha. Let's go with other angles. For example, this one, let me mark it by the way as beta, because the good rule is to mark this one beta, beta. It's just a second to change you alpha, because beta near B, alpha near A, and gamma near C. It's the usual rule that we use when you solve problems in geometry. So gamma, gamma, beta, beta, and let's look at this angle. It's also inscribed here, and it's equal to this angle because subtended by the same arc, and this one is 2 alpha. Okay, let's look at this triangle and let's directly calculate this angle, because we are interested to show that this angle is the same as this angle. Only in this case, these two sides will be equal. Okay, this angle is 180 minus sum of these two angles, 2 alpha plus beta plus gamma, plus beta plus gamma. Great. Just notice 2 alpha plus 2 beta plus 2 gamma is 180, because they are it's in total all the angles of this big triangle. It means that if 2 alpha plus 2 beta plus 2 gamma is 180, it means that alpha plus beta plus gamma is 90. And you can separate it from this sum, and this sum will be nothing but alpha plus 90 degrees. Okay? And the result will be 90 minus alpha. So what you get here, that this angle is 90 minus alpha. And what you need to check, that this angle is actually equal to this angle. Really? Is it true that 90 minus alpha equal to gamma plus beta? Of course it's true, because if you bring alpha here, you will get that gamma plus beta plus alpha is 90 degrees, and we just told that it is definitely true. So these two angles are equal, and it means that ID, let me use black color for this one, ID equals DC equals AD. ID equals DC equals AD. This is it. What's next? It is our result for now, and we will use it to get our final result, and we will get it very quickly, because we had a right solution to extend this chord here. What you have here? You have a chord that passing through the center O of circumscribed circle. Well, it means it's not just a chord, but it's also a diameter. If it is a diameter, it means that this distance here is r, and this distance here is also r. Let's use theorem about two intersecting chords inside the circle. Do you know when two chords intersect, you can multiply like A times B equals C times D. So for example, in this case, this chord intersects with this chord at the point I, and you can say that this segment multiplied by this segment equals this segment multiplied by this segment. Just very simple theorem about intersecting chords inside the circle. In our case, what will we get? We will get that BI times ID, it's the product of two parts of this chord, equals this one times this one, UI, YI times IX, YI times IX. So this one we can rewrite YI is R plus OI, and IX is R minus OI, because you can see OI is the segment that we actually need, and this one, UI, we can rewrite as R plus OI, and IX we can rewrite as R minus OI, As you can see, we have here difference of squares, R plus OI times R minus OI. when you expand the parentheses, you will get that it's actually equal R square minus OI square. It's on the right side. But what do we have on the left side? We still have BI times ID. Let's look closer at this product. BI is a portion of angle bisector. BI in this portion can be easily expressed through the radius of inscribed circle. If you have, for example, let me draw additional picture not to make this one messy. So this one, you have a portion of angle bisector here. It's a BI, portion of angle bisector, and this is the center of inscribed circle. How to find the BI? Easy. So you can make this perpendicular, it's a radius of inscribed circle, and this angle here is beta. And if you want to find BI, you can say that it is expressed through R and beta. In which way? You can just divide R, this radius, divided by sine beta, and in this case you will get BI. It is our result. At first, it is BI. What about ID? Look here, ID, we know that it's equal to DC. It's equal to DC, so ID equals to DC. And what's about DC? DC belongs to this big triangle. And as you can see, this big triangle is also inscribed in a big circle, big purple circle. It means that DC can be obtained through using sine theorem. Sine theorem in this triangle looks like DC divided by sine of opposite angle beta by sine beta equals 2r, where r is a radius of circumscribed circle. Great. It means that from here we say that DC equals 2r times sine beta. And we have the situation that BI here is r divided by sine beta, and ID equals to 2r times sine beta. And as you can see, when we multiply this one, by this one, sine beta cancels out when we multiply these two, and we will get here 2r capital times r equals r squared minus OI squared. And from here we say that OI squared equals r squared minus 2r capital times r, and this one can be represented as r times r minus 2r. And this is it. This is the result that we need. As you can see, the problem becomes very simple only if you come up with the proper picture. And here it's pretty difficult to understand why should you extend this segment OI up to its intersection with the circle to get a chord, but if you somehow do it, the problem becomes just amazing. And in this case, you obviously don't need to consider separate cases, separate scenarios. And by the way, from this formula, you can see that what we have that this is square of some segment. It means that this is always greater or equal than 0. And if it's always greater or equal than 0, or r is obviously greater than 0, then r is always greater or equal than 2 small r. From here we get amazing inequality that connects the radius of circumscribed circle and the radius of inscribed circle. And we can say that now for sure for any triangle, the radius of circumscribed circle is greater or equal than 2 radiuses of inscribed circle. Okay, this is it for today, and thank you.